Hey everyone, this is Daniel for Rock the JVM, and you are watching How to Macro in Scala 3. All right, how many of you have heard about Rock the JVM before? Can you raise your hands? All right, this is beautiful. Thank you so much for following my work. This is going to be a talk on Scala 3 macros, so I have a couple of questions for you before we start. How many of you have a year or less of Scala experience, roughly? Can you raise your hands? Okay, a couple of people. Good. And how many of you have never written a Scala 3 macro before? Can you raise your hands? All right, so this talk is going to be very relevant for you. Okay, so because we're going to talk about Scala 3 macros, I want to talk about programming languages for a moment. Because in order for us to do meta-programming, we need to know how a compiler works and how a programming language works. So I want to ditch Scala for a second, and I want to talk about a much simpler programming language. And I wanted to think of a scientific calculator for doing that. Probably know the kind of stuff, the little machine that lets you write something like 2 plus 3 times 4 divided by 5 plus sine of 30, or something like that. You press equals, and the machine computes the final result, which is whatever this expression is. Now, if you think about it, this mathematical expression, in order to be evaluated, needs to be transformed into some sort of data structure that is predictably evaluated. So, if we want to evaluate this sort of thing, we need to turn it into some sort of data structure. If you want to model that in Scala, you would define some sort of trait. I'm going to define that. I'm going to cut out the import for a moment. I'm going to define a trait that's called this expr, which denotes the kind of stuff that you can express in this programming language of sorts, because you have to fill in a well-typed mathematical expression. And we would define some case classes, for example, like a number which has a value of type double, and this extends expr. And then you have various forms of operations, like a case class for add, which has a left-hand side, which is an expression, a right-hand side, which is an expression, and this extends expression. And then you can copy that and can add operators for subtraction, for multiplication, for division, and then maybe for the sine and cosine, you have a case class for sine, which has an expression of type expr, and this also extends expr. And then you can copy that and you can create a cosine or things like that. So you can basically define all the bits and pieces that you can express in this programming language in terms of this little trait that we call expr. And if you want to evaluate, or if you want to run this program, you would need to somehow build an expression based out of these data structures. So my expression would be, my expr, would be something along the lines of, what do we have here? We have an addition where the left-hand side is a number 2. The right-hand side is another addition, so add. The left-hand side is this little guy, so I'm going to have a multiplication where the left-hand side is number 3. The right-hand side is a division between number 4 and then number 5. And then after the multiplication, the right-hand side of this addition is sine with number 30. This is what we wrote here. So if we want to evaluate that math expression, we would first build that data structure and then evaluate that. If you have that data structure, it's easy to evaluate it. It's easy to write a function that does pattern matching, it does recursion, it traverses that little thing, and then evaluates the final result. Now, this, my friends, is called an abstract syntax tree, or an AST for short. And in order to run any sort of program in a programming language, first of all, you need to turn the text into this sort of thing, into this sort of AST, and then run that. Which basically means that the compilation process of any programming language, so compilation, sorry about the old caps, is basically a text to an AST and then a binary, which then the operating system can execute. This is the compilation process that has essentially been unchanged ever since the first compiler. Even if we have like modern programming languages, the Scala compiler, I think, has several dozen, if not almost 100 microphases that do many different bits and pieces. This scheme has been essentially unchanged. And if we want to do meta-programming, which is the transformation of programs, by the way, for this calculator language, this AST is the program for all intents and purposes. You can pass it around, you can do something with it. Meta-programming is the ability to pass this AST as an argument to some sort of transformation function and return another AST as a result. Now, it turns out that metaprogramming is hard, and many programming languages took different approaches to metaprogramming. Most easy-style metaprogramming involves dynamic type systems and some sort of homo-iconic representation. So for example, if we have the example of Lisp, Lisp is very easy to do metaprogramming, or it's very easy for Lisp to be the gold standard of metaprogramming because the representation of the program and the representation of the data is the same. So you basically have an interpreter that takes the program, which is basically a giant list. That list transforms itself, it becomes a bigger list or whatever, and then the interpreter interprets that. So metaprogramming for these sort of languages is very easy. For a statically typed language like Scala, we need to be able to transform this AST into another AST. But that's basically impossible. Why is that? Because once you have the AST, you're out of the code zone. So it takes the code to build the AST, but in order to manipulate the AST, you need to somehow fetch it back in the code, which is pretty much impossible, which is why other statically typed languages resorted to other forms of code manipulation in the form of compiler plugins or text generators and whatnot. Now, it turns out that in Scala 3, you can do this very easily, or the API allows you to process this AST from the same language, which is absolutely magical. Okay, so we introduced the concept of an AST. Now, in Scala, we have this concept of a macro, which is essentially the ability to manipulate ASTs at compile time. This is super powerful. And a macro in Scala 3 is built out of these phases. First, we need to transform the value into an AST, or the description of the expression that computes that value when run. So some sort of function that takes a value of type A and turns that into an AST of type A, and it turns out that in terms of macros, we have a trait that's very similar. It's called expr, and it has the type parameter. And in the Scala language, obviously, because it's more complex than a simple calculated language, you can express pretty much anything else. You can express class definitions, you can express method definitions, import statements, type definitions, method invocations, the mathematical expressions that we saw here in this simple language, and so much more. So essentially what we do in a macro is to turn A into an expr a process called quoting. Then we do the AST transformation, so we have expr A to an expr B. And this is our logic, and this is the kind of stuff that we tend to do in libraries. So this is where we as programmers tend to operate. And then in the third phase, we turn the expr B back into something that we can then interpret in the code. So we have the expr B back into some sort of value B that we can then use later in the code. And this process is called splicing. So a macro is built out of these three phases. OK. All good so far? Give me like a thumbs up or something. All right, amazing. So I spent like 10 minutes to talk about how programming languages work and how a macro looks like in theory. We're going to spend like the next, 7 hours 50 to talk about what macros do. So let me show you how macros actually look like in the real language. Because a macro is run and interpreted at compile time, we need to have macros in the form of inline methods. So I'm going to have an inline method. I'm going to call this my first macro. And let's say that this first macro takes an argument type whatever, an integer, and returns a string. And if you think about this sequence, if you have A to expr A, then expr A to an expr B, and then expr B back into a B, these are essentially functions that we can compose. So if you imagine that you had three functions, quote of something, logic of something, and then splice of something, we would ideally write something along the lines of splice, of logic, of quote, of my little argument. So this is the kind of structure that any macro will conform to, really. The only thing is that quoting and splicing have separate syntax in Scala, but this is the essential structure. So if we want to write a splice of the logic of the quote of the argument, we would write something along the lines of this. This is the act of splicing. So it has separate syntax. The dollar with curly braces is like code interpolation, which is very suggestive. And then the logic is our separate method. So I'm going to define it separately. So let's say logic. We're going to see the arguments shortly. So logic is whatever. Okay? So I'm going to say logic of quoted code. So I'm going to say quote the expression that I want to transform at compile time. So I'm going to say logic, assuming I can spell properly, logic of, and quoting is as simple as having a single quote and then having the argument. So this is the separate, dedicated syntax for this sort of operation. Now, the logic itself is usually named, if you read libraries or if you browse the code of the magical libraries in the ecosystem, the logic functions are usually called after the macro, only with a little impl suffix at the end. So we have first macro impl, and then we have first macro impl as the function. Now, the parameter that we take in as argument is going to be my argument as an expr int. And this returns an expr string that we are going to splice at the end of the function. So this is the general structure of a macro. Okay, now I'm going to spend, like I said, the next 7 hours 45 to talk about the kind of stuff that you can build with macros. Just kidding. So if you want to build this sort of thing, first of all, you need a single import. And the magic of this macro thing in Scala is that you don't need too many imports. You just need one. And you have import quoted, scala.quoted. And this comes pre-built with Scala. And this function here, first macro impl, if you want to manipulate expressions or if you want to call any sort of methods, you have some sort of macro API that the compiler builds for you at compile time in the form of an implicit or a given value, which is called quotes. It might as well be called macro API or whatever. That's the only thing that you need, and you don't need to use this explicitly unless you use compile time reflection, which is something that we might talk about if we have more time. Okay, so let me show you the kind of stuff that you can build with macros. First of all, let's just use that. So the inline def first macro is going to be run at compile time. So if I go to my macros usage, by the way, if you want to use macros, you have to use them in a separate file, just because of how macros are pushed into the compiler pipeline. You have to use them from a separate file, but that's not a problem if you're using macro-based libraries because they live somewhere else. So we have this macros demo usage where I import the macros demo everything, so I built that in the same package. So if I have a val, let's call this first macro call as first macro with obviously the meaning of life 42. If I save that, that's a compiling error because the first macro actually calls whatever first macro impl was, and obviously because that's unimplemented, the compiling error is very descriptive in that sense. So I'm gonna, I started an SBT terminal here. I'm gonna hit compile just for you to see the kind of stuff that is going to happen. In my build SBT, I have a little flag to say post inlining so that you can see the final code here in the console because these values are computed at compile time. Okay. All right. Now let me do a quick implementation of this first macro impl. First of all, if this expression is an expr of type int, one thing you can do is take the value of that expression at compile time, if it's a constant or a compile time computable value, and do something with it, make some decisions. You may have some constants in your code and you want to set up a feature flag in your application that's usually a global constant or configuration value or whatever, and you want to make some decisions based on that. So we can do something like that. So I can say if the argument dot, and you can extract the value out of it in the AST land, you can say value or abort. So if value or abort is, say, bigger than 3, then you can say expr big, otherwise expr small. Okay, so this is one of the first things that you can do just to take the value of the expression that you use. And look at this, the code compiles. And we can take a look at the SBT output. And the first macro call here, this is the important bit. So yeah, I think for this screen is big enough. But for people watching on YouTube later, it might not be that legible. So I'm just going to zoom in a little bit more. So the first macro call is already computed to be big at compile time. So the first big power that you have with macros is the ability to run arbitrary logic at compile time. Now, the power of macros to run arbitrary code at compile time is constrained to the API that you can use with expressions. There are things that you can and cannot do with expressions. I talk at length in my big macros and metaprogramming course, but this is one of the things that you can do to make decisions based on compile time constants. And it even works with things like 40 plus 2 because the compiler is able to compute this sort of thing and evaluate this sort of simple math expression at compile time. It cannot, however, compute the sort of method, like let's say compute meaning of life, and this is obviously 42. If I call that, if I say compute MOL, this is a compile time error because this is not a constant. So look at this, expected unknown value. That's because I'm using this special function value or abort, which triggers a compile time error if that thing is not a constant. So this is one of the restrictions which are healthy that you have in the macro land. So if you have like 40 plus 2, then that thing compiles just fine. Okay. All good so far? All right, I like the thumbs ups. Okay. So this is something very basic. One of the very powerful things that you can have with macros is to pattern match expressions. And this is mega powerful because you can destructure expressions at compile time and figure out the bits and pieces that you can use to make decisions. So for example, I'm going to have an inline method. Let's call this PM on options. And I'm going to have an inline argument. And I'm using the inline argument because I don't want the compiler to try to compute the value before the method is being invoked. Hopefully I can mount this properly. Okay, so inline option as an option int, and I'm going to return a string, let's say. And you can do op match. And okay, this is going to be the macro function. So I'm going to have to splice PM options, let's call this impl, on the quote opt. This is something that becomes second nature if you start to write Scala 3 macros. You can define a PM options impl with opt as expr option int, and then you can return an expr string. Obviously, not forgetting to use the quotes API, so you can say quotes. And you can do the pattern match, so op match. And the option ints with expressions are pattern matchable very similar to how you would pattern match simple options in the code land in a way. So you can have a case, but the syntax is special and different for macros. For example, you can pattern match the expression itself, which is quote and then curly braces. And for example, if you match sum 42, like this, so literally like this. So if somebody calls PM options on sum 42, this case will match. And this is going to be the expr with, let's say, meaning of life explicitly. Okay? And in case I get something else, I'm going to say expr with something else. Okay, let me go save that. And if I have, let's say, val PM macro call as PM options with sum 42, if I save that, SBT is going to tell me that. So PM macro call has computed this meaning of life explicitly. That's because this case just matched exactly as it is. But if I write something along the lines of, let's say, PM macro call, let's say version 2, and if I don't have the number 42, but maybe 40 plus 2, look at this. We have something else. That's because even though the sum 42 and the sum with 40 plus 2 are actually the same object, the expression itself is different. And this is potentially useful for you if you want to process code at compile time to make decisions. And the pattern matching on expressions themselves, like quote and then curly braces, and then you can pass anything else here. And we spent about 3 hours in the course just talking about pattern matching on expressions and types. You can do very granular processing of code depending on the pieces that you want to use for your application. So if you have a case with a sum with some sort of expression, and the expression can be used with a $sign here, you can process that later. So I can say expression some expression, and then I can inject, okay, let me interpolate that. You have this interpolation in the code land as well, so have some expressions for e.show, for example. Look at this. We have some expression, and then you have the exact thing that the user wrote in the code, 40.plus with the argument 2. So you can destructure this as granular as you want, isolate the instance on which you're calling a method, figure out which method you're calling, figuring out the argument, figuring out the types, and whatever else. So there are many, many things that you can do with pattern matching. And there's something else that I wanted to show you here. So for example, if I have version 3, if I do option of 40 plus 2, even though option and sum actually are the same object at runtime, this is still something else, because the option with 40 plus 2 doesn't match the exact phrasing or the exact expression that was written in the user space code. Okay, so this is some of the stuff that you can use with pattern matching. And I want to show you something a little bit more wild. Hopefully I have some time. All right, 3 minutes is enough. So in my big macros course, I make some projects, and I show you the kind of powers that you can do with macros. So you can do an ungodly amount of things with macros at compile time. So you can process code and optimize it at compile time, which is something that you're going to see here. You can do trace and analysis. You can do type inference or type specializations. You can do, should I say this? You can call a database at compile time, look at the schema of a table, figure out the types and the columns and the values, synthesize new case classes, and then process all the code in your user space at compile time without fetching a single row. So all the type safety and all the power at compile time, you can do that. I don't recommend it necessarily, but this is just an example of what you can do with it. So let me just do a very simple example. So I'm going to have a pattern match on lists. And I'm going to have a list as a list of any, because I don't want to restrict myself to types, and I'm going to return a string. The pattern matching is the important bit. The string is not that important. So I'm going to splice a PM list impl on the quote list, because that's the structure that I'm going to use. And I'm going to mark this list as inline, because I want to pattern match the expression itself. So I'm going to demonstrate the PM list impl on the list as an expr list any with using quotes. And this is going to return an expr string. And what am I going to show here? I want to show you the pattern matching on different kinds of expressions that you can use. So for example, I can say list match. OK, and let's say I'm going to start with an easy case, so an expr with something. OK, so that by code compiles. I want to show that you can process and isolate types. For example, I can say, let's call this list call as PM list on list 123 dot map underscore to string, and then map with I don't know underscore times 3. So repeat the string. Okay. This is something that compiles, and this obviously pattern matches on something, but I can actually destructure this entire thing. Here's how. I can say a case for a quote with curly braces, and then I can say a list with some sort of expression. So I'm going to have an expression which is a list of whatever type, so I can actually isolate the little case t as a type variable, so you can actually inspect the types at compile time as well. And then you can say map to some sort of, let's call this t1. If I have map t2 with some sort of function, and then map with some sort of a t3 with some sort of other function, I'm going to return an expression with an S-interpolated thing, like a multi-map of lists with functions, and then I'm going to say fshow, and then gshow. So I'm actually going to put that at the, nope, not that, okay. Okay, so if you pattern match on this structure, we have list123, map to string, map underscore times 3. These are two functions. And if you take a look at the SBT output, look at this. We have multi-map of lists with functions, and you have the entire thing, the entire representation of this lambda, which is Scala int underscore 12 string. So these are synthesized arguments, and underscore $2, which has the type. So you have all the types, all the signatures, all the implementation, everything else you have here in these expressions, and you can destructure them at will. So if I have a list with some sort of type and map to another type and map to another type, then I can return something else. But you can also have more. For example, you can enforce the fact that T1 and T3 must be of equal types. So you can have a type. So you can define a type variable here. So I'm going to say type T1, which is a subset of any val. And then once you define type variables, in this case, you have to backtick on T1 so that the compiler can assign T1 with whatever the compiler finds at this point. And then if you want to enforce that the T3 must be equal to T1, you can simply say backtick T1 in much the same style as you do with pattern matching on constants in the regular user space code. And that is something that you can do. And in this case, my little double map chain doesn't work anymore because we have list of int, map to a string, map to another string. So the underscore times 3 is actually a string repeating. So we have something here, OK? But if I do underscore to int back, so convert that, look at this. Now we have the multi-map of lists back. So you can do an ungodly amount of safe destructuring of types, expressions, structures, variables, anything else that you can imagine inside this macro land. And I would show you more. I would sit all day to talk to you about what you can do with macros, but I'm going to stop now, and I'm going to take any questions. Thank you so much.